Imagine the Earth, alone, a rogue planet wandering lost in an endless Stygian night. Not even the moon for a companion anymore. No stars to be seen. Imagine it in great detail as a physical reality. The implications are staggering. But one question looms in importance above all others. Exactly how fast is it wandering? Does wandering even have a meaning if there is nothing to wander past? How can you stop and smell the flowers if there are no flowers? This series of audio-visual essays with the umbrella title of The Speed of the Earth examines the meaning of concepts such as relative velocity and absolute acceleration in practical terms, written and narrated by Bruce Mills for the Obligate Pedestrian channel. Measuring the speed of the Earth. To measure the speed of the Earth might be technically difficult, but surely what is being measured has a simple meaning. Despite this assurance, the speed of the Earth is a surprisingly difficult phrase to pin a meaning on. The speed of my car might be 100 kilometers per hour in a 60 zone, according to the speeding fine notification, but the speed of the Earth has no singular definition that would stand up in court any longer than my plea of innocence. Sometimes the speed of the Earth is zero if you take a geocentric approach, and other times it is 30 kilometers per second. Modern cultural law claims that it only has a relative meaning. But what exactly does it mean that it only has a relative meaning? Explaining this requires a lot of unpacking, and it is not as obvious as it sounds. According to modern cultural law, Hendrik Lorentz and Henri Poincaré clashed with Albert Michelson and Edward Morley over the existence of an ether that would give a non-relative meaning to the motion of the Earth. The law explains that, in the 1800s, Michelson and Morley, intent on debunking the ether theory, which was commonly decried as absurd, conducted an experiment that once and for all demonstrated that the concept of the velocity of the Earth with respect to the ether was nonsensical. This is the famous Michelson-Morley null result, which established that there was no absolute frame in which to measure the absolute speed of the Earth. As a result of this debunking, the scientific community became confused because electromagnetic theory said that such a frame should exist. Hendrik Lorentz, who championed the ether theory, then made up excuse after desperate excuse, trying to prop up a clearly failed theory. The scientific community looked on in bemused frustration, but could do nothing, and could not figure this conundrum out. And then Albert Einstein wrote his miraculous 1905 paper that gave the true reason for the null result, and the scientific community breathed a sigh of relief, except for Lorentz, of course, who ended his days in insane denial, having been ostracized from the scientific community for his continued belief in this mystical luminiferous ether. Let that be a warning to those who would follow the path of pseudoscience. At least, this is as the cultural law would have it. However, to paraphrase Einstein himself, this is so far from the historical facts and context as to be grotesque. The demise of the luminiferous ether. People have measured the speed of a sound, the speed of a bullet, and the speed of a cornoaspersum without deep-seated controversy. Why should measuring the speed of a planet have produced so much confusion, conflict, and cultural law? Why has it generated cranks and crusaders? Why can it start acrimonious argumentation on Facebook groups? It is just a big ball of hot rock, after all. In many ways, it all hinges on a few hours that passed at Mount Wilson Observatory in the United States in February 1927. A few hours that are not often heard about today. Hendrik Lorentz was there. He was a well-respected leader of physics at the time and had chaired the Solvay conferences, and in October that year would chair the very famous gathering where Einstein and Bohr argued over what God did with dice. Somewhat accidentally, many of the luminaries of the luminiferous were at Mount Wilson at that time. The observatory seized the opportunity to hold an impromptu conference. It was simply titled, "On the Michelson-Morley Experiment." At this conference, a certain interpretation of events was voted on informally and declared retroactively to be history. Lorentz died soon after, at the start of 1928. This was a great handicap to his espousing his own view of the matter. History is written by the survivors. Conclusions voted on by the survivors became the unquestioned cultural law, which was handed down to those of us around at the beginning of the 21st century. Rewind this story to the mid-1800s. Hendrik Lorentz was born in 1853. At that time he was not yet dead. In respect of this essay, not a lot else happened in 1853, but the very next year James Clerk Maxwell graduated from Trinity College in Cambridge, in England, as a mathematician. 10 years later, during the 1860s, Maxwell would complete the work on electromagnetics, for which he would become internationally famous across time. It is in the works of Maxwell that the real trouble begins, or at least becomes apparent. The work by Maxwell on electromagnetics was strongly, but not uniquely, inspired by the work of Michael Faraday. Faraday was famous for having developed a theory that combined electricity and magnetism. Electricity and magnetism had been thought of as two distinct essences, but he described them as projections of a single electromagnetic essence. It was a theory based around physical intuition and mental visualization of bundles of lines permeating all of space. These intangible lines originated and terminated on electric charges wrapping around currents and magnets. Although based on a geometric intuition, the theory of Faraday did allow calculation of explicit numerical values for practical measurements and the development of numerous practical demonstrations and tools. He was a popular lecturer at the Royal Institute, in particular at the Christmas and other public lectures. But despite all this, his work was criticised at the time as being only intuitive and not precise or rigorous. In 1855, when Lorentz was a toddler, Maxwell, knowing of the work of Faraday, wrote a 76-page monograph on Faraday's lines of force. He converted the ideas into precise algebraic and analytic mathematics. Maxwell also borrowed from the work of others and added some interpretation of his own. But the effect of this was to provide a strong algebraic construction of the theory of Faraday. Maxwell himself stated that Faraday was clearly an excellent, albeit unorthodox, mathematician. Similar controversy over what is mathematics has arisen at other times, for example in regards to the work of Moritz Escher. Was Faraday a consummate mathematician? Probably not in the direct sense. He was a physicist and he often used physical reasoning. However, this judgment is very much dependent on the shift during the 1600s from basing mathematical work on geometric principles to basing it on algebraic principles. So there is some pure semantics in the judgment. Regardless of whether he was a great mathematician or a great physicist, Faraday's work was very practical, so perhaps he was an engineer. He worked directly with the laboratory and always checked alleged electrical and magnetic facts in laboratory on the spot. Everything he did, even when accused of being whimsically abstract, was driven directly by measurements that he could and did perform in the laboratory every day. The theory of electromagnetics is directly driven by things that we can touch and feel and repeat in our own homes with very little equipment. Without this very important point, nothing that follows in this exposition will seem to have any purpose. Almost everything is electric. Although Maxwell had written about Faraday and about electromagnetics in 1855, his investigations continued to evolve for more than another decade until the end of the 1860s. Faraday himself was suffering from senility and died in 1867 when Lorentz was starting his life as a teenager. During this time, something new emerged clearly from the theory. It was possible to extract from electromagnetic theory a differential equation analogous to the ones describing the motion of waves. The speed of these electromagnetic waves could be determined mathematically. While Faraday appears to have considered this idea earlier, Maxwell derived it rigorously and determined the speed of this wave directly from quantities relating to the strength of electric and magnetic forces as measured in the laboratory. The curious point was that the speed computed for the electromagnetic wave was very close to the speed measured for light. This suggested the possibility that light was an electromagnetic wave. It would have had to be very high frequency to explain refraction, but the behaviour matched. This idea that light was electromagnetic was part of a general slide towards the principle that all of physics was implications of the theory of electromagnetics. Static electricity was electromagnetic, magnets were too, but so too, apparently, was chemistry, in that Humphrey Davy had demonstrated that electricity could cause a chemical reaction, and earlier Alessandro Volta had shown that chemical reactions could cause electricity by the process of taking numbfish apart to see how they worked. Humans have a history of taking other animals and even each other apart, ostensibly to see how they worked, but not learning much, not even learning how to put them back together. What was rather impressive is that Volta actually succeeded in figuring out the modus operandi of the electric organ and duplicated it on the laboratory desk. The upshot is that all material seemed to be electrical material. Later, subatomic reactions would need theories that were distinct from electromagnetics, but these are fairly natural, albeit non-trivial, mathematical generalizations. They flow directly from the principles initially laid down for the behavior of electromagnetic fields. Poincaré explicitly noted this principle when he was working on developing the theory of general matter in the early 1900s, and by Lorentz in developing the theory of the electron. The odd one out was, and still remains, gravity. The principle of Galileo. Galileo de Vincenzo Buonanotte de Galilei, popularly known as Galileo, was born in 1564, 3 centuries and 10 years earlier than Hendrik Lorentz. He is often referred to as the first modern physicist. The ancient Greek Aristotle spoke of motion in terms of a tendency for objects to be in certain places. Galileo was determined to relate a theory of motion to directly measurable features of the world. He focused on time and distance. He measured in several different ways the distance covered by different objects over different times. Galileo developed the principle that the acceleration of an object under gravity did not depend on what it was, in particular on how heavy it was. This later became one of the core principles of the Einstein theory of general relativity. The historical records suggest that Galileo was the first to strongly promote the idea that velocity was only relative. Einstein relativity is often touted as being different from Galileo relativity. However, it is arguable that if Galileo had happened to have access to the theory of electromagnetics, he would have seen Einstein relativity as a valid implication of his own thoughts on the matter. He might have been freaked out by the implications, but he would have seen the point. The reason, however, that electromagnetics of the 1800s clashes strongly with the relativity of the 1600s and leads to confusion over the velocity of the Earth is not at all apparent from this discussion so far. But it will be explained in visceral detail in further installments in this series of audio-visual essays. Review of the concepts. The idea that velocity of an object is only to be measured with respect to another object is commonly given lip service in modern culture. It is a thesis of this series of essays that this cultural law does not come with a sufficient understanding of what it actually means. Keep in mind that although in modern physics it is accepted that velocity is relative, it is also just as accepted that acceleration is not. Sometimes this point gets confused in translation to common language. People will point to the idea of measuring relative acceleration and claim that this means that acceleration in all motion is obviously only relative. However, the point here is that it is actually a mere mathematical tautology that any motion can be measured in a relative sense. There is no deep concept there. What is the deep physical principle is that absolute acceleration actually can be measured every time you are swung sideways as a car turns a corner. So the fact that in practice velocity cannot be measured in an absolute sense is a strange mystery that has to be resolved, and not an obvious idea that must be true. This is a major point that will be investigated in later chapters. The start of this investigation is to understand the notion of an ether that might have given an absolute velocity to the Earth, and why things did not work out quite that way. It is not as simple as to say that the ether theory was only accepted by ignorant savages who had not thought this through. Indeed, the final form of Lorentz ether theory, in terms of computation and terms of prediction, is identical to the Einstein relativity theory. Yes, ether theory was actually never debunked. What occurred was a change in philosophy and methodology, not a change in what the theory predicted. In fact, ether theory is mainly a point of view on classical electromagnetics that tends to lead towards extensions such as quantum field theory. The details of this point are available in the older literature, although many modern physics textbooks repeat a mythology of events that came into vogue in the 1930s. The relativistic principle of Galileo is often contrasted with the relativistic principle of Einstein, as though they were very different. Actually, both of them worked from the common idea that velocity could not be determined from local experiments done in a closed shipping container jettisoned by the Vogons in deep space. The distinction is that the ambient physics of Galileo was closer to what is known as Newtonian mechanics, while Einstein used Maxwell mechanics. It is in the ambient physics where the distinction arises, and not in the principle that velocity is relative. It turns out that Maxwell mechanics, that is, laboratory electromagnetics and its quantum extensions, such as quantum electrodynamics, which have been confirmed again and again with every electrical device, generate some very unexpected results when combined with the principle of relative velocity. These points will be expanded and clarified in later chapters. Whenever I said historical records, I couldn't help thinking of Galaxy Quest. In The Incredibles, Gilbert Hupf, backed into a corner regarding a matter of policy, responds with, "The law requires that I answer no." I am often reminded of this response when I am speaking of the dominance of cultural law. That is LORE, of course, and not LAW, But I think that the principle is the same.